The basic goal of physics is to understand how things behave, which means we need to know the laws of mechanics. Now, we already worked out the laws of mechanics in the classical mechanics section of the course, and those laws must be at least approximately correct because they predicted the world that we saw very well. But the other thing that laws of mechanics have to obey, we now know, is the principle of special relativity. They must be the same in all inertial reference frames. Now, the only theory we know that actually behaves like that, the only classical theory we know, is electromagnetism, which is no surprise because that's how we discovered relativity in the first place. But now we've got to go and look at all our other laws and make sure that they also obey the principle of special relativity. We're going to start by looking at our basic conservation laws. So the first thing is that if something's going to be conserved in all reference frames, then it's going to need to be a scalar or a vector. And so if we're going to look at, say, our momentum, we can't use the 3 momentum, just the px, py, pz as the mass times the velocity, because that is not a 4 vector, and therefore it's not going to transform the right way. But looking at that, we might guess that for a massive particle, the 4 momentum might be just the mass, which is some kind of scalar, times the 4 velocity of that particle. And as we recall the definition of our 4 velocity, this is just where we've defined this to be the relativistic momentum. So you'll note the relativistic momentum has a factor of gamma as well as the mass times the velocity. But we have this time-like term, which is gamma times m times c. So let's try and figure out what this term is by expanding it to lowest order in the velocity. Now we can expand this using the binomial expansion. And if we take it a factor of 1 on c, we get things that we recognize. Okay, so in other words, we particularly recognize that this is the kinetic energy. So up to a factor of c, remember we've got a factor of c between the time-like and the space-like coordinates usually. So up to that factor of c, we've got the kinetic energy. So just as special relativity is unified space and time, the sort of the vector and that scalar, it's also unified momentum, the vector momentum, and the scalar energy. And so this 4 vector here is not just the momentum 4 vector, it's the energy momentum 4 vector. And we should be unsurprised to see energy and momentum being unified like that. Remember, energy was the generator of time translations, and momentum was the generator of spatial translations. And so if we actually have space-time, then energy momentum is going to be the generator of space-time translations, and they should be together. So in a universe where the Lagrangian, which we'll have to generalize in order to be a relativistic Lagrangian, but it's some scalar in our universe, where the Lagrangian is not changed by space-time translations, then we would expect the total energy momentum to be conserved. Now, of course, although we spotted the kinetic energy turning up here, there's also this rather large offset term. And Einstein was the first person to realize that this large offset term might actually be physical. In other words, that a piece of mass might contain energy simply from the fact that it exists. And so if we assign this entire term to be the energy rather than just the kinetic energy part of it, then this energy momentum tensor becomes energy on c and the momentum. Then we recover one of the most famous equations in all of history. E equals gamma mc squared. If we look at the norm of the 4 momentum, then that's the same number in all reference frames. So if we take the inner product of the momentum in itself, then we're going to get these terms. So we're going to get the energy squared minus momentum squared. But we can calculate this very simply in the rest frame. So in the rest frame, all of these velocities are 0, and the gamma is 1. And so this term here is just mc. So one way we can relate the energy and the momentum is like this, where this is the magnitude of the relativistic 3 momentum. And so you have this relationship between the energy and momentum, and so if the momentum and the energy are individually conserved, you can use this in relativistic problems to calculate the magnitude of the energy. And although we worked all of this out for a massive particle, this actually also holds for a massless particle, so we could look at our 4 momentum like this. So there's our relativistic 3 momentum, and there's the magnitude of it popping up there. And this indeed both hold even when the mass is 0. And so if you have, for example, the mass of a photon, then if you know the momentum, then you know the energy. So you can use that to do kinematics problems very easily. The other thing you need to know to do a kinematics problem properly is you need to know that the 4 momentum is conserved. In fact, usually it's the total 4 momentum that's conserved. So if you have more than one particle, then you have to add up the 4 momentum of each particle, and they're all conserved, collectively at least. And because that's a vector relationship, just like with normal vector equations, each component is individually conserved, so the energy component and each of the momentum components are conserved, giving you effectively 4 equations. If you're particularly astute, you might worry that if you have differing numbers of particles, if you have particles that are splitting up or joining together, then you might not actually know what to sum over. Here's a space-time diagram, and supposing we have a particle zipping along and it breaks into 2 particles. That probably doesn't conserve momentum as drawn, but you can see what I mean. If it breaks into 2 particles, then you can imagine if you have lots of these things happening, then if you want to know what form momentum to add up, of course you have to know at what time you can add them up. And you might say, hey, I'm going to add them up at this time here, but remember, this is only these 3 particles existing on this axis. This is only simultaneous in this frame. There's another frame where, in fact, you can slice it that way, and you'll see that you actually have 4 particles there. And so that's a little bit concerning until you realize that the very fact that this form momentum is conserved means it doesn't matter how you slice up your space-time, you'll still always get the same value for the form momentum. So it's conserved in all frames.